Hello there, Earth Science students. Dr. Shragi here, and I am giving you a little review session in ahead of your Module 6 test. I thought I'd give you a little tour of the things that have available to you on Google Classroom and show you I've made you a better review sheet and give you more information about that. So let me just real quick walk you through here on Google Classroom. As always, it's better to be in the classwork tab than to be in the streaming tab, although I've noticed some people do try to make this work for them. Personally, the streaming tab is not my favorite thing. So if you go over here to the classwork tab, you can see that we've got a whole bunch of stuff that we've done here in Module 6. Now, as you scroll down, you may actually have a place where it says, let me just see here, like for example, over here, mine says view more. You make sure you watch for that, okay? Because that is a little bit hidden in Google Classroom. But on Module 6, you should go all the way back to composition of the atmosphere. And composition of the atmosphere, you might recall, was a reading assignment that you did. In fact, I think it's the only explicit reading assignment that you did for this chapter. Now, keep in mind, it's always a good idea to read the chapter. There's only certain times of the semester that I grade you on reading it, but obviously always it's a good idea to have read it. So for this reading assignment, you were doing sections 16.1 and 16.2, and those are very definitely on the test. So if you need to go back and review those or take a look at the questions and stuff that were back here, that'd be a good idea. Remember, that was the day, for example, that we learned about the differences between weather and climate. I can assure you that there are questions on the test about the differences between weather and climate. We learned about the nature of air. We learned, for example, that air was best described as a mixture. It's made up of different gases that have been stirred together but are still chemically separate. Oxygen, O2, is not the same thing. It has not been chemically combined with nitrogen. They're just together in the mixture that is air. I like questions. Well, okay, like this one here was asking you for what were the three most abundant gases in the atmosphere. The word dry here means we're forgetting about water vapor for right now. And so the big three in the Earth's atmosphere are nitrogen, oxygen, and argon. You add those three up and you have 99% of the Earth's atmosphere. All right, let's see here. This question, actually, 16.6, is interesting because this one gets to the heart of the business of the greenhouse effect. The greenhouse effect is hardly a major emphasis in this module, although it is certainly something that we talked about briefly. And you learned that carbon dioxide was absorbing Earth's emitted energy and keeping it from being emitted back out into space, trapping it on the Earth's in the Earth's atmosphere. Now, it's different from what ozone does. Remember, ozone is a form of oxygen. It's actually O3. We breathe O2, but O3, which is a nasty toxic gas, is unfortunately, well, for good or for bad, it's necessary for life on Earth because it absorbs, I don't like this word filters out, it absorbs most of the ultraviolet radiation. Ultraviolet radiation, remember, is really bad stuff. It causes skin cancer and crop failures and things like that. As it happens, most of the ozone that does this is in the layer of the atmosphere called the stratosphere. And this would be a good time for me to mention to you, to remind you that this business of the layers in the atmosphere is definitely going to be on the test, but we'll see a little bit more about that in just a bit. We learned on there as to why ozone was important because it reduces risk of things like skin cancer and such from ultraviolet radiation. We learned about at that time the Montreal Protocol, which was a way of reducing the impact that we were having on the greenhouse effect. Montreal Protocol is not on the test. This is actually showing how carbon dioxide is a variable gas in the atmosphere. The term variable constituent of the atmosphere will certainly be on the test. Water vapor and carbon dioxide were our major variable constituents of the atmosphere. Everything else was a constant constituent. Pretty much wherever you went in the Earth's atmosphere, you came across the same amount of oxygen or the same amount of nitrogen or whatever. But carbon dioxide and water vapor aren't quite like that. Make sure you know this vocabulary word aerosols here, how tiny solid and liquid particles suspended in the atmosphere are called aerosols. That's a good word to know. Anyway, that was a reading assignment that we did way back in October, in early October, if I'm not mistaken. All right, so if we cut back here, I'm going to leave this here. After we did composition of the Earth's atmosphere, over fall break, one of the lectures you had to do was about vertical structure of the atmosphere. Now, I would recommend, again, one great thing to do would just be do the readings. I mean, there is a section in the book, I think it's 16.3, but I could be wrong, that describes the structure of the Earth's atmosphere. Certainly going back and looking at the exit ticket again would be a great choice because a lot of the questions are going to be quite similar to that. Let me just sort of dig through the vertical structure of the atmosphere PowerPoint here with you a little bit. Now, we in that lecture, I encouraged you to skip the first part of it here that was about contours. We actually ended up doing the contouring lab in this time period, but we'll associate that with the oceans stuff rather than the atmosphere stuff. So I know some people did actually watch this part of the lecture here that was about contouring and also about how this Greenwich Mean Time and stuff works, but you didn't have to do that. That was actually just that part of the lecture was to be skipped if you hadn't already. So if we skip that first part of the lecture, we just go to vertical structure. We're going to be talking about how features in the Earth's atmosphere change with respect to height. By features, I mean things like temperature or pressure or humidity. And with height, I mean like how they go up in the atmosphere. So like as you get higher in the atmosphere, how does temperature change? Or how does moisture change? Or how does temperature change with respect to height? And well, one easy one to talk about was pressure. Because pressure is, again, much like we talked about it many other times this semester, because pressure is about the weight of the air above you or weight of anything above you. Well, as you get higher and higher up in the atmosphere, there's less air above you than there was before. So pressure can only decrease with respect to height. And so like on this diagram here, we see on the y-axis height, and on the x-axis is a measure of pressure. And we can see how pressure starts out quite high near the surface, and as you get higher and higher up in the atmosphere, the pressure always goes down with respect to height. We actually learned a little rule here that won't be on the test that explains how much it's decreasing with height. But I mean, just because we can't get everything on the test, but that's a good thing to have learned. Another feature that we learned was about moisture, how moisture changes with respect to height. And this, we had to think about it. Well, most of the time, moisture is going to decrease with respect to height. It has to do with where we add water vapor. The source of water vapor, the place where we are getting water from that we add to the atmosphere, is at the surface. It's mainly in the form of evaporation off open bodies of water, like oceans and lakes. So the source of water vapor at the surface of the Earth is at the surface. So that's going to be where there's the most water. Whereas, like if you go higher up in the atmosphere, that's where water vapor gets turned back into liquid water. It no longer is water vapor anymore. It gets turned back into liquid water that might fall out in the form of rain or whatever. That's a sink of water vapor. So as a consequence, most of the time, we have a lot of water vapor at the surface and very little water vapor up aloft. So most of the time, we would say that water vapor decreases with respect to height. And we actually had this little analogy here about kids in the pool. You might remember how there was pee in the pool and all that kind of good stuff. Anyway, we won't worry about all that here. So most of the time, like on this graph right here, where we have measures of the amount of water vapor on the x-axis and the height of the ground, you can see that generally speaking, as we get higher and higher above the ground, the amount of water vapor is getting closer and closer to zero. All right, these little practice questions that are embedded in the lectures are always great things to use to study. That's why they're there. All right, now let's see here. We're going to be talking about temperature too. Now, if we make a similar graph of temperature, where we saw how temperature changed with respect to height, we saw it kind of zigzagged all over the place. There was a layer of the atmosphere where temperature decreased as you went up, and then a layer of the atmosphere where it increased, and then a layer of the atmosphere where it decreased, and a layer of the atmosphere where it increased. And in fact, that turned out to be a useful way to sort out the atmosphere into levels and layers. We had 4 different layers here. The lowest one, where temperatures generally decrease with height, was called the troposphere. And it goes up to about 10 kilometers or something like that. That kind of number isn't on there. Above the troposphere, temperatures increase with respect to height. That's, by the way, includes where the ozone layer is inside the stratosphere. Then above the stratosphere, we had the mesosphere. We're getting pretty high up in the atmosphere now. I mean, far higher than jets and things like that. We're talking like 90 kilometers up or something like that now. But in the mesosphere, the temperature decreases with height, and then finally up here in the thermosphere, this goes way high up, maybe to 500 kilometers or something like that. The International Space Station is in the thermosphere. I know you think the space station's in space, but the thermosphere is, the gas. All right. I am being told by my thing here that I have to stop in 29 seconds or something like that. I didn't realize I had a shortened version of this, so there'll have to be multiple parts to this video, which is fine.